Okay, so we considered the idea of z squared using trigonometry. I suggested that you could use the trigonometric patterns that we utilized in the last lesson to find a z cubed, and said that with a little bit of work you can end up with r cubed cos 3 theta plus I sine 3 theta. The question is, what happens when you get to z4, z5, z6, and is there a pattern? Now, to consider that pattern, we're going to look at the relationship between E and cos and sine. This relationship can be found with the Maclaurin series. That is to say that the Maclaurin expansion of cos theta plus the imaginary multiple of the Maclaurin expansions of sine theta is equal to e to the I theta, if in terms of this also being expanded as a polynomial by way of Maclaurin. And so this is the relationship. You'll find that this expanded plus this expanded in terms of the Maclaurin series, or their Maclaurin series, is equal to the Maclaurin series of e to the I theta. What we can then do is we can say, well, let's ask for there to be a multiple of these, a multiple of, in terms of n on both sides, and then we can utilize ABC is equal to AB times C, which means we can switch these about. So I'm going to switch the theta and the n to produce n theta. If you look at the relationship between the angles, this theta is related to this theta in sine, and this theta here is related to this theta in cos. That relationship is very important because that is literally what allows for this plus this to be equal to this when you analyze the Maclaurin expansions or the Taylor expansions about the point 0. Now, in these x-axis 0, and in these, so when you consider this, you then can go, okay, well, what is this? This is a scenario where I'm just going to put a multiple of thetas. So if there was 10 degrees, now it could be 20, 30, 40, 50, 60 if n were integers, and not being limited to integers in this discussion. So if that is the relationship, if this is 30 degrees, these will be 30 degrees. If this were 40 degrees, these would be 40 degrees. If this were 45, these would be 45. So if these were n thetas, then so will these be n thetas. So that is to say that this, we can suggest that this relationship must be true. Now, one last thing we can consider is, again, utilizing this rule that ABC is equal to AB multiplied by C in this area here is equal to AB times C. And so, in a sense, when there is a bracket, whatever is outside the bracket can be switched with whatever is in. Hence, I can say that this is the same as E or Ni theta. This is the same as Ni theta, and I theta is cos theta plus I sine theta. So if I zoom out, what I'm pretty much suggesting is, why not substitute, if I can use a color here, why not substitute this cos theta I sine theta is equal to e to the I theta for this in here, by way of suggesting that this is something that looks like that. So I've taken the ei theta is cos theta plus I sine theta multiplied separately by n. So I've said, okay, let's take the n out. And so that little substitution, that ability to move these around, a2 times 4 or a k times b or whatever letters you want, if there is a bracket here, they can be moved around as comfortably as any level of multiplication. So instead of considering I n theta, I've put the n in front, change this to n I theta, where an e to the I theta is cos theta plus I sine theta multiplied by the n. And not to overdo it there, you can always write this down and consider this further for yourself. But generally speaking, I've not changed the right-hand side. That is still the same idea. The right-hand side is cos n theta plus I sine theta. And then you are left with this lovely little relationship here, also known as de Moivre's theorem, in which what it's suggesting is whatever the power is that cos theta plus I sine theta are having to undergo, whether it's they're having to be multiplied by themselves twice or 3 times or whatever, it is equal to cos a multiple of the angle in here. And this is not, it should be relatively intuitive, given that we've just had a conversation that suggests that when you had z squared, you simply had to add the 2 angles. When you have z cubed, I suggested you have a go at that yourself. You simply have to add the 3 angles. Z4, you're going to have to add the 4 angles. Z5 and so on and so forth. This pattern can be considered as multiplying whatever this value of n is in terms of the n here. So if n was 2, then it would be theta 1 plus theta 2. If n was 3, and so on and so forth, 3 times theta. Now we can come to this conclusion as we did before. If z1 is r1 cos theta 1 plus I sine theta 2, and z2 is r2 cos theta 2 plus I sine theta 2, then when you multiply these together, you have to multiply the moduluses. That's r times r, as shown here. You have to multiply those, and you have to add the angles, as shown here. You add the angles. The arcs get added. The additional thing that we've learnt is that if you have, or what we said again, is if you have the z cubed equals r cubed, you end up with r cubed cos 3 theta plus I sine theta. And most powerfully now, if you have z 4, 5, 6, 7, notice that when I say that, that's because this whole thing in here is z. Z 3, 4, 5, 6, 7 in terms of power will be cos 3, 4, 5, 6, 7 in terms of angle. And that is de Moivre's theorem. To conclude, what we're going to do is going to look at this problem. This is known as de Moivre's theorem. We're going to use it. We're going to look at a problem that utilizes de Moivre's theorem. It pretty much says that z to the power n is equal to rn cos n theta plus I sine n theta. Now, this is the question that we're going to tackle. Simplify cos 2 pi over 9 plus I sine 2 pi over 9 to the power 2, and here it's to the power 4. I want you to think about this, and we'll come and tackle this in the next video.